Hello, Professor Schumacher here. Today I want to show you a demo animation written in VPython that should help you understand how optical pumping works. This is a method for manipulating the spin states of certain atoms. In our case, we're working with rubidium. So if you want to follow along, we'll look at this demo, and if you want to try it for yourself, feel free to download it from the address shown at the bottom of the screen, the QR code on the right if you'd rather, or from the information given on the metadata of the YouTube file. Here is our list of things that we're going to talk about. And let me just start at the top by showing you the layout of this demo so you can get an idea of where we're going with all of this. So here's where we are at the beginning. Notice the box over here. Now let each of the green arrows represent one of the rubidium atoms, and the arrow itself represents the direction of the spin polarization of the hyperfine substate of interest that that atom has. The long blue arrows are supposed to represent the external magnetic field against which the spins of the rubidium atom are lining up by virtue of their magnetic moment. The yellow panel at the bottom, that represents the incoming circularly polarized light that's shining at the atoms. And here at the top, we have the detector that is detecting how much of this light from down here is reaching the top. This green arrow over here is the vector sum of all these spin arrows over here. So in a sense, green arrow here represents the overall spin polarization of the entire sample. If that single spin were the only thing in the problem, then we could break that down into the quantum mechanical F equals 2 hyperfine substates. And right now you can see that this arrow is pointing almost straight up, which for us represents almost all the amplitude of that state being in the m sub f equals plus 2 substate. Meanwhile, down at the bottom here, we have, as a function of time, we have the ensemble average of all these green arrows, which, as I've been talking, has been growing exponentially to the maximum possible value. That's the overview of the visuals in this demo. And now we'll proceed a little bit and do some of those steps a little more slowly. Now, you probably noticed I went rather fast here. So my next point is that if you want to understand the physics of optical pumping, this video is really not going to teach you that. You have to learn this separately, not from this demo. But once you've got the basics in mind, then I hope that this will give you a better sense for how things work. So in particular, you need to educate yourself about the hyperfine level splitting of the atoms, in particular the rubidium atoms used in our discussion here. The light that's going to shine on these atoms, there are certain quantum mechanical selection rules for the absorption and the emission of light from these atoms. And there's this trick that allows us to pump the atoms all to be in the same quantum state. So you have to understand the selection rules for making that happen. Then there's the phenomenon of Larmor precession, where we can apply a radio frequency magnetic field to induce the atoms to rotate away from the original magnetic field direction, which has consequences for the amount of light that comes through the sample. As part of that, we have to understand how circular polarization of light arises. This trick only works with circularly polarized light, and that has something to do with angular momentum transfer. So indeed, all of these things you need to proceed to learn, and once you do and get at least a start on that, you'll understand much better what we're about to see. So first, let's look into the question of light absorption and emission in quantized steps. That's what's going to lead to this phenomenon of optical pump. So here we are. I have turned off the light down here that is shining onto these atoms, and I did that by clicking this button that says pumping on and off. So right now there's no light shining through the sample, and initially you can see that the orientation of the spins is fairly random with respect to this external magnetic field and with respect to the direction that the light will go through the sample. Down here, the ensemble average of the spins here is very, very small, so they're more or less randomly placed right now, okay? So nothing's happening yet. But now let's turn on the circularly polarized light that's going to shine from the bottom to the top. And we're going to do that with a click here. Boom. Okay, here now the light is on. Notice the red flashes on the atoms here. This is supposed to simulate what happens when a photon, a circularly polarized photon that has +1 unit of orbital angular momentum or spin angular momentum striking the atom, it has the effect of moving the atom up 1 unit of magnetic substate, and that atom can then stay in that excited state for some time, a brief time, nanosecond time scale, and then de-excite back to a lower level that has either the same or +1 or -1 quantum number of magnetic substate. But on the average, you're going to push the atoms up to higher and higher energy levels, because for every absorption of a photon, that's going to always push the atoms up 1 step. So they get pushed up 1 step, and then they either stay there or they go up another step or they come down a step. But on the average, they're always going to be increasing their magnetic substate number. So in aggregate, as time goes by, here's where we turned the light on, you can see that there's this exponential rise of magnetization or spin orientation of the atoms in this sample until this is supposed to represent 100% magnetization or spin polarization right there. And so you can see how the ensemble average has gone from nearly 0 to maximum value up here. So that's step number 1. Okay, so next we're going to look at the question of dealing with the oscillating radio frequency magnetic field that we can apply in a way that allows these spins to precess at a certain frequency, and that will change the overall spin polarization of the sample in a way that is visible on your oscilloscope to see how the pumping effect is modified when we apply this oscillating RF pulse. All right, so let's start again. So here we have the light turned off down here because I clicked this pumping button to the off position. And all the spins are aligned. That's because I hit the reset spins button up here that makes them all align perfectly with the external magnetic field represented by these blue arrows here. Now, they'll stay this way forever unless we hit them with some magnetic field that will make them change their direction. And so what I'm going to do is turn on this sideways oscillating magnetic field and explain as we go what's going on. So this button will turn on that RF oscillator. Boom, there we go. So now please imagine this this arrow right here oscillating back and forth. This is our representation of the cosinusoidal magnetic field that we can induce with these red coils right here, which I'm sure you can find the analog of these in the actual experiment that you're hopefully doing. So what's going on? Well, initially the spins were pointing up, right? But now the oscillating magnetic field is oscillating in the horizontal plane here. And so as soon as the spins get knocked off the vertical direction a little bit, they start to precess around the few Gauss of vertical magnetic field that's there from the get-go. And so when you knock them off that direction, the spins will, as they say, precess around the external field direction. And so as time goes by, we can see this oscillatory net ensemble average of the alignment of the sample with respect to the vertical direction. So it goes from 100% aligned here to being totally anti-aligned, and then back to the first direction, and then in an oscillatory way back and forth. So that's our demonstration of the effect of what's called Larmor precession on the spins of the atoms in the sample. Starting this once again, I next want to show you that if the frequency of this oscillating field, which by the way you can also see this magenta arrow oscillating here, that frequency has to be matched to the frequency at which these spins want to precess. The external magnetic field, the big blue arrows, that magnetic field, which in the experiment is a few Gauss, right? So you need to match the precession frequency of the spins with the oscillatory frequency of the externally applied RF field. If the frequency is not right, which I can change by, say, pushing this button that says raise frequency, then you see that the matching is no longer perfect, and the spins don't precess all the way around anymore. So this is because, as we say, we are no longer on resonance. So when the RF frequency matches the precession frequency of the spins, then you are said to be in magnetic resonance. And we've just tweaked the thing so that we are not in perfect resonance anymore, and the spins do not precess all the way around. So we can fix that. There's another button here called lower frequency. I will tweak that. Yes. So there you see, we are now back in resonance, and the frequency is matched between that at which the atoms want to precess and the RF frequency that's being applied from the outside. So you have control both of the strength of the external magnetic field, and you have control over the frequency of the RF field that you apply to establish the magnetic resonance condition. Now, what we were just watching had the pumping process turned off. Now we're going to turn on the pumping process and see what happens when these so-called quantum spins versus the classical spins are also doing their thing of absorbing and emitting light. Okay, so here we are at the beginning again, and I've turned off the pumping light, and I will now take the spins, which are all aligned, and I will apply an oscillating RF magnetic field, and we do that by clicking this button here. Okay, so there we go. But now we turn on the pumping light and watch what happens. We turn on the light, and you can see that things start looking a little crazy, right? So in other words, every time there's a red flash up here, that's our simulation of a photon being absorbed by the spin and promoting it in a quantum mechanical sense to the next highest level of magnetic substate, and that means it's pointing a little more in alignment with the external magnetic field represented by the blue arrows. And so as time goes by, more and more of these spins are on the average going to be pointing upward. That is the optical pumping effect, because as we tried to say a few minutes ago, every time an atom absorbs a photon, it will bump up its magnetic quantum number by 1 unit, which means it's slightly more aligned. It can then give away that excitation energy in a way that either leaves the magnetic quantum number alone, or raises it by 1, or decreases it by 1. But on the average, the polarization or alignment of that atom gets increased as time goes by more and more. So let's start the process over again. And here we start with a random ensemble of spins to start with. They're essentially unpolarized at the beginning. But the light, as time goes by, strikes more and more of the spins and pushes them more and more into the orientation where they have maximal spin projection in the direction of the incoming circularly polarized light. You can see the growth of the polarization vector over here, and you can see the exponential rise of the net polarization here. So this is one of the things that can be measured in the experiment. If you look for how to do it, you can watch this exponential rise and see what the characteristic pumping time is for the ensemble of atoms that you are using. Then we mentioned a few minutes ago that if we have the RF frequency tuned correctly, then we can rotate the direction of these spins and change the amount of light that actually gets all the way through the sample, and that is reflected by the change in the net polarization down in the lower graph. So let's make that happen, turn on that oscillating field. And while that's happening, I'll mention that one of the things that is usually done in this experiment now is you can match the oscillating RF frequency, which you have control over, and you know what the strength of the vertical magnetic field is. That's another thing that you have control over. The ratio of those numbers is something that you can use to compute the so-called quantum mechanical G factor for the atoms that are in the sample. And so that's one of the typical goals of the experiment that you can do here. You can measure this quantum mechanical property of rubidium atoms, do that by sampling the behavior of the system for different frequencies and computing the magnetic field within which the atoms are processing. Starting again, let me talk about the connection between these classically represented spins here that have this net polarization over here, and speak about the connection to the quantum state that corresponds to this classical picture. If we have all of our atoms in this m sub f equals +2 state, that's like saying they're all aligned with the external field here. And if we now turn on the RF oscillator so that these states collectively spiral down and spiral up, you can see in this little panel over here the quantum mechanical projections of the states onto each of the 5 eigenstates of the m sub f equals 2 system. So we have the different m substates, and if we're pointing straight down, then we're in the m sub f equals -2 state. If we're pointing straight up, that's the m sub f equals +2 state. And when we're in between, we're somewhere in a superposition of all these quantum substates. That's very important to understand, because it turns out that the classical vector here is correctly represented as, in the quantum world, as a superposition of the 5 amplitudes that are available to the quantum system. So it's not the case that the atoms are in some kind of always Z projection, but different magnitudes. It is perfectly correct quantum mechanically to think about the spin polarization to be, shall we say, sideways, but that simply represents a superposition of the 5 possible substates that are measured along Z, but which collectively represent a state that's pointing in some desired arbitrary direction, including in the XY direction, not just in the Z direction. Finally, let's take a look at what we mean by the Rabi oscillations. We saw these in passing a few minutes ago, but now we're going to actually name them and show you what they are specifically. So we start again, and we have the pumping turned on, and we're supposing the spins are all aligned to start with in this part of the story. And so now let's turn on the oscillating RF field, which causes the spins, if they're in resonance, to start to precess. And you can see that the alignment of the sample dives to some negative number, and then it comes up back positive, and you notice it starts to oscillate. Okay, so this is the phenomenon we're chasing here. What's happening is that as the spins are precessing, the light is striking them. Those are the little red flashes up here that indicate the spins being struck by incoming circularly polarized photons. And so they start to get out of step with each other on account of that. So the net polarization doesn't go all the way from +1 to -1, back up to +1, back down to -1, but it dies out slowly. So these oscillations are named after Isidore Rabi, who in the years following World War II did a lot to explore this phenomenology of spin precession and so on. So these fading oscillations here are named Rabi oscillations. That's the phenomenon that we're seeing. And so you can see what that does to the net polarization here. And as time goes by, the coherence of the sample will die away completely. So in these experiments, one can measure some properties about the sample by looking at the decay rate and the spacing of these oscillations, these so-called Rabi oscillations. So in this very fast demo, there are things that we haven't mentioned and which you should really either read up on your own or ask your instructors. So we only touched on the question of how classical spins are related in this demo to the quantum spins of quantum physics. And it is a fair thing that we've done, because the time dependence of the expectation value of the quantum spin operators is really the same as the time dependence of the classical spins when they move in a magnetic field. So it's not a fake. This is a faithful representation of the quantum physics in this problem. We haven't talked at all about what is the hyperfine level splitting in atoms. We didn't talk about that at all, and we don't know how to enumerate those levels. So that's a whole separate thing that you should learn. And we mentioned but didn't explain quantum selection rules for absorption and emission. I just said in passing several times that circularly polarized photon with, say, +1 unit of h bar of angular momentum will always increase the spin projection of an atom by 1 unit, and then there are selection rules for the re-emission of that energy that are also respected. But you can't learn that from a quick demo like this. We didn't really talk about how Larmor precession is related to the magnetic moment of the atoms. So a bit more quantum, or really classical physics there to make that connection between Larmor precession and angular momentum and magnetic moments. That's a nice connection that we didn't really talk about. And we didn't really explain how light comes to be circularly polarized in the first place. And so this whole trick only works with circular polarized light. So you might want to investigate that in due time. Okay, so in closing, thanks for your attention to our very rapid demonstration of optical pumping of rubidium with this VPython demo. Again, you can download it and play with it yourself at more leisure in order to explore the different effects that are being represented here. And thanks for your attention.